So homework, are we up on the screens? Those seem weird. Real? All right, so we're adding another ability to our fraction class to teach it how to add a fraction to another fraction. Okay. Here's our fraction class here. So we're going to go into the fraction class itself. And just as a reminder, remember we make everything private, and then we give ourselves the ability, accessor ability, either through read only for a getter or read or write only through a setter, or give yourself both. So we have these guys private. And then we currently don't have a way of directly accessing those things, but this actually becomes kind of an interesting piece to this. So right now we have the ability for a fraction to display itself. We've also made it compatible with the println method using that toString method that we talked about last class, how all objects in the entire Java language come from that top level object class, which comes with a toString method. So if we wrote our own toString method inside of our own objects, println now knows how to call it. All right, it's built into println. Not that you ever have to do this if you don't want to. This is more of just a parlor trick that if you want it to be compatible with println, you can make it compatible with println. So now we have, so this guy, if I just kind of put some comments in here, make our object compatible with system.out.println. This would be that version of that guy. All right, because remember println, if we went into the system, went to the print stream class, which is what kind of value out was, there's a whole bunch of println methods that were in there. Remember we talked about that being called polymorphism, a class with the same method with the same name, but a different number and or type of parameter. All right, so println is one of those guys. So giving ourselves our own toString method that happens to return a string and is public will override the one that came with the object class. And then we also gave this guy the ability to display itself. So now we're going to give him a new ability. So we're going to give him the ability to add himself to another fraction and return a fraction as a parameter. So we're going to return a fraction. We'll make it public. We're going to return a fraction. We'll call this guy add. It's going to take another fraction as a parameter. See, in the game, somebody would have said something. Are you okay, buddy? All right, so we're going to teach this particular fraction how to add themselves to another fraction, returning a fraction as a result. All right, rather than having this guy take in two fractions. All right, so you know, beginning programmers might be they say, oh, I need two fractions in order to work. I do have two fractions here. I have this dot numerator, this dot denominator. That's one of my fractions. And then I have another fraction numerator, another fraction denominator. All right, so first thing we need is a common denominator, right? So easiest way to get this is to multiply the two denominators together, right? So we'll say, and I think I made these guys longs, right? So we'll say long common denom is equal to this dot denominator multiplied by, now here's where things get a little interesting. Denominator is a private variable. And I want to get another fraction's denominator. Am I allowed to do this? I could say this dot denominator. Why am I allowed to do this? Go ahead. Yeah, so go back up. Remember, what does private mean? Private means that this variable is only accessible from within inside the fraction class. So I'm in the fraction class, and yes, this is a different instance of fraction, but it's still the fraction class. So we do have access to that guy's private fields because we are inside the fraction class. Almost like we have special permission. Okay, close relative. All right. So we're allowed to say another fraction dot denominator, even though that guy is private. We didn't have to write something like get denominator. So that'll give us a common denominator. Now we want to get our numerators. So we're going to update. So we'll say long num1 is equal to this dot numerator multiplied by another fraction dot denominator. Long num2 is equal to another fraction dot numerator multiplied by this dot denominator. So that was our cross multiplying. All right, so now we want to build a new fraction. That is our answer. So fraction answer is equal to, so remember when we build a fraction, the constructor wants a numerator and it wants a denominator. We have to give it those two parameters. So my numerator for this fraction will be num1 plus num2, the addition of my two after I made these guys compatible with my common denominator. So this will boil down to a single number, num1 plus num2. And then my denominator will be my common denom. So this allows me to add this fraction to another fraction, spitting out even another fraction as the answer. So we'll go ahead and test this guy. So we have our couple of fractions, f1, f2. And we'll go ahead and say fraction sum is equal to f1 dot add f2. So f1, just as a reminder, the add method here does not have static out front. So since it does not have static out front, it's owned by an instance of the class. So we need to call it using an instance of the class in which this method was defined. This method was defined inside of a class called fraction. So we call it using an instance of the fraction class. f1 dot add f2. Then we can say sum dot display and get our answer. Oh, I never actually returned it. I promised here with the add method that I was going to return a value, and I didn't. I got the value I want to return, but then I need to actually return it. So there's my answer, 10/8. Now notice here, if I just change the F1 to F2 here, and the F2 to F1, I'll get the same answer. The same two fractions are involved. I just am calling the other guy's version of the add method and then passing the other guy in as a parameter. Make sense? Okay. So it is technically two different versions of the add method. One of them knew everything about F1. The other one knew everything about F2. And we had to provide the other fraction as a parameter to it for it to work. All right, make some sense? All right. So now the next thing we might want to do is 10/8, even though it's the correct answer, we might want that guy to be reduced. Give us the lowest common denominator. Okay. Now, we might say that it never makes sense for a fraction to be used in anything but reduced form. Fair enough? So we might say that a fraction should always be reduced in order for it to be most usable. With that in mind, if I want to teach my fraction class how to reduce itself, if I want a fraction to be able to reduce itself, it would be reasonable for me to give it the ability to reduce itself, but make that ability private. Only have that ability accessible within the fraction class. So I could come in here and I could say, I'm going to write a private function. And this guy's not going to return anything. What he's going to do is he's going to internally modify the numerator and the denominator, put it into reduced form. Okay. So we're not going to have it return anything. We're going to call this guy reduce. He's not going to need any parameters because he already knows about this particular fraction's numerator and denominator. Why? Because it's not a static method. It's an instance method, so he knows about the instance that calls it stuff. All right, make some sense? All right, so reduce means we need to find the value, the greatest value that evenly divides both the numerator and the denominator. So let's write it in the most straightforward programmer way first. So these are kind of the puzzle type things you expect to run into like on midterms and things like that, especially since you have a time requirement. It's hard to write 3 different classes and do a bunch of stuff with it. And I know this is overlap from last semester, but this kind of gets us caught back up on the programming stuff. So if, for example, we wanted to take 10/8 and we wanted to reduce that, we want to find the greatest value that evenly divides 8, but also divides 10. So the very first thing we might do is we might say, okay, well, what's the largest possible value it could be? The largest possible value it could be will be the smaller of the numerator and the denominator, right? All right, so I'm going to ask a question. So we'll say long largest possible. And let's just assume I make a guess. I'm going to say this dot numerator. Actually, let's say this dot denominator. It's probably the better guess. Actually, no, this dot numerator is probably the better guess. Chances are the denominator is bigger than the numerator, like 1/2. 1 would be the largest value that even possibly could do it, right? 3/8, 3 would be the largest value. So we'll guess numerator, but nothing says we can't have a fraction like 5/3. That's a legal fraction. So we may have guessed wrong here. So we're just going to ask a little question. We're going to say, if this dot denominator is actually less than this dot numerator, if I guessed wrong, I'll go ahead and set largest possible to the denominator. Make sense? You could have also just written it as an if else. But I think this is every bit as efficient. Like, look, it's probably the numerator. Was I wrong? If yes, fix it. Otherwise, leave it alone. All right. So now I have the biggest value it might be. So my job now is to count down from that value potentially down to 1, because I know 1 will evenly divide both of them, right? The numerator and the denominator. So I want to count down from this largest possible value all the way down to 1, testing each value to see if it evenly divides both the numerator and the denominator. All right, a for loop that's going to count down. So maybe for it I is equal to largest possible. That's where we'll start it. Keep going as long as I is greater than or equal to 1. We know, as a human being who knows math, we know it's going to kick out at 1. It'll finish there. But that also means that we didn't actually change it. So we really could say greater than 1 and just not even do anything with the 1, because anything divided by 1 is going to be itself. So we can say I is greater than 1, I minus minus. We're going to try all the values down to 1, hoping that we find at least one of those values that evenly divides both the numerator and the denominator, because that means that we have now been able to reduce our fraction and that we actually need to do the reduction. So we're going to ask the question, if this dot numerator, when divided by the current value of I, has a remainder of 0, and this dot denominator, when divided by the current value of I, has a remainder of 0. If both of those things are true, then we're going to go ahead and say this dot numerator is equal to this dot numerator divided by I. This dot denominator is equal to this dot denominator divided by I. And then we're going to say return. Remember, well, this guy does not return a value. Its return type is void. But remember, the return keyword makes a method immediately end. It does not require us to actually spit a value out. If we were returning a value like we did here, this guy was expecting to return a fraction. So I made the method end and I spit out a fraction. In this particular case, I'm just making the method end. I've done the damage. Make sense? I've gone through, and if I just hit the largest value that even divides both of them, I'm going to fix my numerator and denominator locally, and then I'm just going to get out of Dodge. I don't need to spin through this for loop anymore. Similarly, if I didn't want to use return, I could have said break. What the break keyword does is it gets us out of the most recent for loop. So that would just put us on this line right here. And then the method would naturally end on the very next line. You can decide which one makes the most sense. In this case, I don't have any other logic to do. So I would say, if you don't have anything else to do, just get out of the method. Otherwise, if I was going to do something after the for loop, before I just let the method naturally end, I would break out of this for loop and then go ahead and do any extra logic I was going to need to do. All right, that makes some sense. So now we have taught our fraction class how to reduce itself. But notice if I come out here to main and I say sum dot reduce, it's going to scream at me. It's going to say this guy has private access. You can't externally tell sum to reduce itself. That's for internal use purpose, internal use only, right? Kind of at the bottom of some of those forms you fill out at doctor's offices and stuff like that, you know, for office use only at the very bottom. So this is not something that the end user, the public facing user, is going to be able to utilize about our objects, but it's something that inside the object might be handy. Because now what I can do is inside the fraction class, I might say inside of add, before I return my answer, I might say answer dot reduce. I could also just return the reduced version of answer if I wanted to. Actually, no, that wouldn't work because that boils down to nothingness. So I'll tell my answer to reduce itself first, then I'll return the actual answer. Now, similarly, we could do this at the constructor level too. Nothing says that our end user couldn't build the fraction with a 10 and an 8, right? They could pass in 10/8 for the fraction they're building. And then we can just internally go ahead and say this dot reduce. So now in a couple different places inside of our code, we've called upon this function to reduce stuff. And what I mean by that is if I say fraction f3 is equal to new fraction 10/8, for example. Actually, let's make it 16/10, just so it's a different value. And then I say f3 dot display 16/10 is going to be what, 4? So this will, yeah, so it'll be 8/5 divide it in 2. Probably should have flipped these over, so because typically we wouldn't have a numerator, it's bigger, but we'll just roll with it. Oh, I still have this guy here. Oh, I made largest value. I must have made it an int. Yeah. Because it's possible, since largest possible was a long, it's possible that value would actually be too big to fit inside of an int. Technically possible, because longs can hold up to 64 bits, and int can only hold up to 32 bits. So it is possible to have a numerator that is larger than a numerator or denominator that's larger than an int. So if I'm counting down from that guy, I need to make them a compatible data type. So we see here that it actually went ahead and instantly reduced my fraction, even though I built it as 16/10. Inside the constructor, I'm calling reduce. So even though I built it with 16/10, it's going ahead and reducing it for me. And we see that we actually have 5/4 coming out of that 10/8, because now add is also calling reduce at the end before it's done. Where's add? Add's reducing the answer. Make some sense? All right. Now, if you remember from last semester, we did see I introduced a time complexity problem with actual reducing fractions. In our case here, we're reducing a pretty small fraction, no harm, no foul. Let's see if I can. Say 2 to the 63rd. That's not going to give me a. All right, really big number is the numerator. Slightly smaller number is the denominator, but gigantic numbers. right? That technically should fit inside of a long. Now, since we are reducing inside of our constructor here, as we are building this guy, as we're building our fraction F3, and we try to reduce this fraction, it's going to take a very long time. Unless I just happen to pick numbers that evenly divide each other real quick, real early on in it. But having these giant numbers, we should be good at least down to half, which is going to take some time. So this is a time complexity problem. We're actually getting the greatest common divisor of a numerator and a denominator, greatest common divisor of two values, is actually very time consuming. We actually have a better way of doing this. And we're going to be able to see this if I run this code. We're going to see that we don't even get to display our first fraction because this guy's still chugging. So go ahead and run it. Do I have to throw long in front of it? I need to tell them it's a long. It's signed. I did to the 63rd, didn't I? Yeah. So we should be good on the value. So how do I pass in a int of the right size? How do I tell it this guy is a long? Actually, an interesting question. My literal is a long, not an int. So I'm going to put an L at the end of it. The who what? I would think it'd still be okay. Well, we could probably fake it here. Let's say long A is equal to this guy. Let's see if I get past that line before I go any further. Yeah, no, it doesn't like that either. It won't let me put a value. I think we should still be good even with just a bigger value. See how far I have to cut it down. Million, 20 million. Yeah, thanks. All right, there we go. At least we're proving the point. Clearly taking a long time, but that is actually a very interesting. How do we force a long that is that big, or do we need to internally just keep adding until we get to it? There's got to be a way to do it. All right, so we all are convinced it took extra time in order to do that. All right, good enough. Interesting trivia question. If somebody wants to tackle that, figure out the way to accomplish it, that would be a very interesting problem, I think. I'm sure there's a solution to it. You have to be able to represent long literals. Okay, so the issue here is that we need to have a better way of representing the reduced function. And we looked at this last semester. We'll go ahead and do it again real quick, just because it's not going to take real long to do. We have this Euclidean algorithm. Somewhere in here, it's going to show us what the pseudocode is for it. So this is all the math proving why it works, yada, yada, yada. All right, so here's the actual greatest common divisor function. So you pass it two values, and it's going to boil down to the value that is the largest value that evenly divides both of these guys. All right, so we're going to go ahead and we're going to write a function called GCD inside of fraction. So we'll say private long GCD, and most languages probably have GCD built into it in some sort of math library. Java probably has math.gcd or something like that, but we'll write it ourselves. So this guy's going to take in a long A and a long B. Something representative of our numerator and our denominator, more than likely in our case. All right, I chose A and B because that's what the algorithm out here is doing, so we'll be able to copy it directly. So as long as B is not equal to 0, while B is not equal to 0, we're going to do some stuff. What's the stuff we're going to do? We're going to create a variable called t, set it equal to b. So t is equal to the current value of b. Then we're going to set b equal to a mod b. We'll update b to be equal to a, the remainder of a divided by b. Then we'll set a to be the old value of b, which we preserved inside of t. Yeah. And we're going to keep doing that over and over and over again until we finally whittle b down to 0. Once we've whittled b down to 0, we can return our final answer, which is stored inside of a. All right, if you're interested in why this works mathematically, you can go read the top part of that Wikipedia thing. But bottom line is, this is the Euclidean algorithm that Euclid came up with, as well as a couple of other people disconnectedly, but whatever. That will efficiently find the biggest value that divides two integers. So now what we can do, we'll just write a second version of reduce here. We'll say void reduce 2. All right, and what we'll go ahead and say is we're going to say long max val is equal to this dot GCD of this dot numerator, this dot denominator. We'll pass in our numerator and our denominator. It's going to do the crazy algorithm stuff, and it'll spit out the largest value that divides both of those. So we'll say this dot numerator is equal to this dot numerator divided by max val. This dot denominator is equal to this dot denominator divided by max val. And that's it. So now that we have the GCD function, That reduce function is much simpler, keeping in mind that we still have this logic that's still occurring. So if we call reduce 2 in here instead of reduce, similarly in our constructor, if we call reduce 2 instead of reduce, we come back out, we run this guy, we'll see it runs very quickly. Good. Mm-hmm. And it does work. Okay. But I did set wrong. Okay. But so what did you do? 17? Yeah. Oh, yeah, thanks. Although we saw how fast that happened. Actually, that did happen super fast, and it would have had to count down quite a bit in order to get this. So bottom line is we see the GCD working. It's way better than doing it our hard-coded way. Now, for us in here, and the reason I kind of remind us of this from since last semester, it's not about learning the GCD algorithm. It's really more of a awareness for us that sometimes we might solve a problem in a straightforward way, a way that made sense to us, like we wrote reduce the first time. And it may end up, we might end up stumbling into something where technically our solution is accurate. It did the job. It eventually got the right answer. But because of some circumstance behind the scenes, this one being a good example, it is a very complex problem that does take a lot of time, even for really, really, really fast computers. And there could be an improvement, an optimization using some alternative way of doing it. Okay. Now, what's going to be interesting about this, the reason why this is interesting for us is I would say an extremely high percentage of the time, the most inefficient solution to something won't feel substantially slower than the most efficient solution to something from a programmer's perspective. Most of the time we're writing code, write it in a way that makes the most sense to you. Write it in the most accurate way that still makes the most sense to you. Don't necessarily try to highly optimize it just because you think you're supposed to. Nobody's impressed if you have an extra 2 lines of code, or you got the curly brace, you save yourself 1 line, whatever it is. But be prepared that every now and then you might run into a situation where you're like, I'm really confident that this should work, and I don't know why it isn't, or why is this taking so long? And you might initially think, oh, I must be stuck in an infinite loop. And if you start looking to see if you're in an infinite loop and you find, I'm really not, keep in the back of your head that you may have stumbled into one of these problems where it might actually matter that you write it a little bit more optimally. Okay, but I'd still always encourage you, when you're first writing the code, to write it in the way that makes the most sense to you, not in the way that you think will be the most optimal. A correct unoptimized solution is always better than an incorrect optimized one. Okay, makes some sense? All right. Questions about any of that stuff? right, so I'll go ahead and save that. And I don't know if this gave me the same link, but I'll go ahead and put this on Slack here. And we're going to create a new project. We're going to revisit what we were doing right at the end of last semester and then build on top of it. So I don't know, do we call it just dungeon crawler or something like that? What do we call it, mud? All right. So what we were working on at the end of last semester was this idea of a mud, multi-user dungeon. So Dungeons and Dragons, early computer game stuff that later has graphics and stuff, but we're not going to write the graphics for it in here yet. But the idea is that we want to pick up where we left off and then start adding stuff, get into some new things. All right, so if you remember correctly, we had a whole bunch of rooms that were linked together, right? So we have a collection of rooms linked by exits. Rooms have a collection of exits. And initially where we left it off, and potentially a player. Now, ultimately, we're going to get up to this point pretty quickly. So ultimately, what we're going to do is we want to have the ability to have monsters and stuff like that inside of our dungeon, where we can go into a room and maybe have a fight with a monster. Now, we also then want to get to the point where, hey, you know what? Maybe a monster has the ability to wander around the dungeon too. Or even if we're just standing in a room, you might have a rat come in, you know, something like that. So we want to see, how do we write code that ultimately does that, where we have, you know, the game feels alive in a text-based way. so something like that. All right, make some sense for the angle we're going with this. So hopefully we can kind of get caught up to where we were right at the end of class. I'll go relatively quick now that we've had our introduction to objects in Java, and then we'll start adding some stuff to it, talking about inheritance and some other things like that. All right, questions, comments, concerns, bribes. All right, no homework for Wednesday. I will see everybody then.